All right, let's begin this. These are the answers for the practice problems for test two. All right, so definitely you want to go over these. The test two's part B questions are exactly like these. Okay, they're just different numbers. All right, so here we go. Let's work on this first one. It says a moon rock sample is brought back by the Apollo astronauts. And they give the mass of it in kilograms. Uh, in this case, it's 0.974 kilograms, and its volume is carefully measured to be 295.15 cubic centimeters. What is the density of the rock in grams per cubic centimeter? All right, so I'm going to write the equation for density down. So the density is given the symbol rho. Let's see, let me make that a little bit thicker here. Is given the density rho. Sorry, it kind of looks like a P, but it's a Greek letter. All right, so rho is typically the letter that's used for density, and density, of course, is mass divided by volume. Okay. Um, so we have to, you have to know what the volume is, you have to know what the mass is. Now they give us the mass, in this case it's in kilograms, but in this particular formula we're going to want the mass to be in grams. The volume's already in cubic centimeters, it says that right here, so we don't have to change that at all. All right, so really this is just a matter of changing the units of the mass. All right, so let's do this. The mass of this rock sample is 0.974. All right, kilograms. And so we know, right, just from our metric prefixes, that 1 kilogram, right, a K anything, whether it's a gram or a meter or whatever, means it's 1,000. All right, so 1 kilogram would be 1,000, which I'm going to write as 10 to the third power. That's supposed to be a three. Sorry, 10 to the third grams. All right, so that's supposed to be a G. All right, and so the kilograms cancel, right? The kilograms cancel, and so you just take the 0.9 uh, 0.974 times 1,000, and so this of course becomes 974 grams. All right, so that's as simple as that. And then now the density, right? The density of this is going to be equal to the mass in grams, which is 974 grams divided by the volume, which, by the way, usually you have to calculate the volume, but in this particular case, it was given to us. This would be 295.15, and it's centimeters cubed. All right. All right. So now we're ready. So we're ready to calculate this. All right. So this answer is equal to, and I already have it up here. It should be 3.3. All right. So let's see what that is. All right. So here's my calculator. So 974 divided by 295.15. All right, and so there it is. So 3.3. All right, it's 3.3 grams per centimeter cubed. All right, so and remember in Blackboard you just type in the numerical value, and it said to round it to one place past the decimal. It says that right there. All right, so that's the answer to the first one. Um, 3.3. By the way, that is also the density, the average density of the moon, as a matter of fact. So not just that one particular rock from the moon. The entire moon has about that density. And so what that means, by the way, is that the density of the moon, the there are things that are a little bit more dense than 3.3, and there are things that are less dense than 3.3. It averages out to be 3.3. All right. So just like, for example, the Earth has a density of 5.5 grams per cubic centimeter. So there's stuff in the Earth that's more dense than that, and there's stuff that is less than dense than that, like liquid water, for example. But it averages out to 5.5. All right, let's go to the next one. All right, so just here's the next problem. Like everything in orbit, our moon travels in what's called an elliptical path. All right, so it gets close. It gets closer, it gets further from the Earth, so slightly closer and slightly further. The point where it's the closest to the Earth is called the perigee. This is just some extra information. When the moon, let's say that the moon was at perigee in this picture that I've just drawn. That what that means is if the moon were a full moon at that time, if the phases of the moon, put it as being a full moon, then and it's the point where it gets closest to the Earth. That's actually what we call. You'll hear sometimes they'll talk about this on the weather. That it's a super moon, right? A super moon. It looks slightly bigger. It's never the news makes a lot of they talk about, oh, go see the supermoon. It's never really that much big. You can't really tell that it's that much bigger. They just kind of make a big deal out of that on the news. I don't know, 'cause maybe it's a slow news day. Who knows? All right, so here's the basic idea. All right, so here's the situation. Suppose we have a radar beam that travels from Earth, from the surface of the Earth. All right, so here this is going to be our radar beam. So it's going towards the moon, right, and then it hits the moon and then bounces back, right, and so this is it coming back. All right, so this is the radar beam coming back. All right, and they give us that the round trip time. So the time to go there and come back, right? So this is T, I'll call it T round, right, or TR. The round trip time is 2.422. 2.422 seconds. All right. And so really what we're interested in is the time it takes the radar beam to get to the moon. All right. Of course, not if you're not on the moon, you don't know when it gets there. You just know when it gets back, when it bounces off the moon and comes back. At any rate, the time, radar, just like all forms of electromagnetic radiation, travels at the speed of light. All right, which is such a special number in all of physics and astronomy, well, in all of the physical sciences. This is such a special number that it gets its own symbol. It's called C. All right, and so the value of it is 3 times 10 to the, well, it depends on what we want here. So normally it's 3 times 10 to the 8th meters per second, or you could write it like this. You could say 3 times 10 to the 5th kilometers per second. All right. So, and the reason that I just did this is because they want to know what the distance is between the surface of the Earth right here and the surface of the moon right there, in kilometers. See, it says it right there that it should be in kilometers. All right. So, so we have this equation. I mean, this is the basic idea. The speed of anything is equal to the distance that thing travels divided by the time it takes to travel. All right. Now we know that the time here, the time is going to be half of the round trip time. So t in our equation is going to equal half of this value. Right. So we're going to have to divide this by 2. All right, and which we'll do in just a second. All right. So And this formula, of course, is given to us, on the equation sheet. This is the uh, again, this is the basic equation for velocity. As long as something's not accelerating, it's not changing its velocity, and the speed of light does not change. It's just a nice constant 3 times 10 to the 5th meters kilometers per second, or 3 times 10 to the 8th meters per second. All right, so if we take this equation right here and we rearrange it for and solve for d, which is really what we want to do, just look at this equation here. Here it is right here, and you just multiply both sides by t. All right, so t and then t. All right, so what you do to one side, you got to do the other. So the t's cancel, and so we have what d is equal to. So d is equal to the time, the time that the radar beam takes to get to the moon, which is, of course, half the round trip time. All right, so I'm going to just put that. So it's going to be 2.422 seconds divided by 2, right? Because that's the round trip time times the speed of light, which is 3 times 10. I'm going to use the e for 10. This just means times 10. Times 10 to the 5th. Of course, it's kilometers per second. Kilometers per second. And so notice the seconds cancel, and that'll just leave us an answer in kilometers. All right, so let's see what this comes out to be. All right, so let's get my calculator here. All right, let me move that so we can see it a little bit better. All right, here we go. All right, so let's start with the time. The round trip time was 2.422. And then, of course, we divide that by 2 because that's just the time to get to the moon. All right. And then we multiply that time times the speed of light. All right. So times 3. Remember, with exponentials, with scientific notation, I should say, you don't ever hit times. You don't ever hit 10. You use either this EXP button, or if you have a Texas Instrument, it's the EE button. All right, so anyhow, EXP to the 5th. All right, so there we go, and there's our answer right there. So the answer is 363,300 kilometers away. All right, so that's how at that point, when the moon is at perigee, that's the distance to the moon. So it's 363 and then 300 kilometers. All right, so that's how you do problem number 2. All right. The one thing, don't forget, when you're given the round trip time, and you just want to know the distance between those 2 points, you divide that by 2, as we did, right here. Right. That's why we divided it by 2. All right. Very nice. Where's my? All right. I'll do the next one in the next video.